Hello everyone and welcome to the Python Exchange. My name is Cameron Riddell and I will serve as your host for today. We all know that the Python Exchange here is our community-driven series where we bring together researchers, developers, and tool builders to share how they are using Python to push the boundaries in both science and engineering. And if you are interested in staying in the loop with us, you can find us on our website. That's meetup.doepy.org. I'll paste that link in the chat once we get going for you all. Additionally, you can also keep in touch with us by finding our newsletter on our website or just coming in the chat and saying hi during our Q&A session. Today, we are joined by a fantastic guest panelist. We are joined by one whom you even might recognize, that is Janssen. Jan leads the Materials Informatics group at the Planck Institute for Sustainable Materials, where his team combines atomistic simulation with modern computing tools like machine learning and large language models to accelerate materials discovery. Jan is the creator of pyiron, which he has told us about before. And I will say, Jan is also here to talk about executorlib. That is a minimalist Python library for scaling scientific workflows to HPC and exascale systems, all while keeping things light, fast, and easy to debug. And so, Jan, with that in mind, I'm going to go ahead and turn things directly over to you to help us get started. Jan.
Perfect. Thank you so much. So let me share my screen. You should now see my presentation.
Perfect.
And then you see the presentation?
Yes.
Okay, perfect. Good. Yeah, thank you so much for the introduction. As said already, my name is Jan. I'm the group leader for Materials Informatics here at the Max Planck Institute for Sustainable Materials. And today I want to talk about upscaling Python functions for high-performance computing with executorlib. So in my work in the Materials Informatics group, we really try to bridge the gap between material science and computer science, really the materials part, and try to leverage a lot of the technology that is available from the computer science, including more recently the machine learning techniques. So we really want to go here from the atomistic simulations up to the predicting of the material properties, and we leverage a lot of Python here, and in particular the high performance computing. So I want to use the following few slides to give you a rough introduction of first how we work and different open source projects that we were involved in, and then come to the challenges that we see in particular with the generation of exascale computers and how a library like executorlib can really simplify this process. So the first project that we were really primarily involved in was the conda-forge project, because we always struggled with this challenge of installing material science software on our computers, right? And conda-forge made this very easy. And so seeing how easy it is for standard mathematical libraries, we contributed by now over 900 packages for the materials science domain. And this really was an initial push, which now led to even more people from our community contributing their packages on conda-forge. So in total, we reached something over 400 million downloads. So that's quite an impressive number for a rather small community. Once we had the software installed, and that's what Cameron already mentioned, and I guess I presented here roughly 3 years ago around the same time, is the pyiron framework, where we heavily relied on the Jupyter Notebook and later on Jupyter Lab environment to really have the full process of setting up an atomistic structure, the idea what we want to simulate, and then also the setting up the simulation, running it on an HPC, analyzing the result, and even plotting the final result in a figure, all inside one Jupyter Notebook. So previously, this was a very distributed task on our side, where some parts were happening on the supercomputer, other parts were done maybe on the student's laptop. And so it was very hard to track the progress. And by moving everything to the Python level, we were able to really have a full workflow documented inside one Jupyter Notebook. And more recently, this has been extended to really inside the material science community, trying to find a joint format between different workflow managers like Jobflow and AIDA and our pyiron tool to really represent workflows in the same way. I want to show this just to highlight a bit how close we are as a community already to the pyiron open source community and in the material science domain. Pyiron, for example, is also a NumFocus affiliated project. So we really try to give something back from our domain, also more general. And I hope maybe executorlib can follow in the same footsteps, being useful also to scientists outside our domain. So now for the next few minutes, I want to take the chance to give you a very brief introduction what kind of simulation we do in material science and where we see the huge opportunity of these simulations and why we need so much computing time, and in particular Python computing time, to do this. And here's a typical challenge that we face in our work, right? So let's take a look at magnesium. Magnesium is very lightweight. We would like to use it for many different applications, including cars, for example, but it's rather brittle, right? Already at 10% compression, you see it here in the picture, it fractures. We can't use this in an engineering application. The reason for this is what is known as dislocations. You see them as these black lines moving through our material. As long as they move, they are not so bad. But when they stop at a specific point and more dislocations pile up at this point, that's when it fractures. So that's where we get this brittle behavior from, and then the material can't be used. On a theoretical level, this can be understood that in magnesium, there's the basal plane and the tensile twin plane. On those two, the dislocation can move, but there's no other plane, and that's much less than we have in a typical crystal or other materials. And it was also known before our work that if you put something like yttrium in there, where you activate a third, this pyramidal slip plane, then you suddenly can compress the very same material up to 50%. Right? So we see a drastic change in material properties, while it's still primarily magnesium in this alloy. And that's really the challenge. The disadvantage of magnesium is it's a rare earth metal, so it's not so easy to get, and we want to replace it with other elements. And that's where our computer simulations come in. Right? So we now want to iterate over the whole periodic table and find other elements which have the same properties as yttrium when we put them into the magnesium alloy, but are much more available and it's less costly as, for example, adding yttrium in our magnesium alloy. So we see this here. So we have the periodic table, and we look for a 3-component alloy together with magnesium. And if we filter this by, let's say, 95% similarity, we see that it's already much sparser, right? Only the yellow spots are the elements compositions that are presumably relevant. And there are some like the lanthanide and actinides, which might be relevant, but which we can't use for the engineering applications because they're nuclear materials and we don't want to use them in our cars, for example. And if we filter by solubility and then also the cost part, there's basically just a single alloy that survives. That's the magnesium with 1% aluminium and a 0.1% of calcium, right? So it's a little more than 1% that we change in terms of material, but we can also compress this up to 50%. And even more important for me as a simulation person, this was not discovered first experimentally, but we did the simulation, we predicted this material, and afterwards our experimental colleagues were able to validate this and really find this material. Right? So we're really now at this point in the material science domain that we can do electronic structural simulation. So we really start with the quantum mechanics that you know from university, and then predict new materials, and our experimental colleagues find them exactly where we predict them. This is more recently also then extended by including what's known as machine-learned interatomic potentials. So we now build a very diverse set of a lot of different structures that we want to include in our model. We then fit different potentials. You can think about a potential as the interaction between two atoms. And now it's how strong this interaction is depends on the environment around this atom. So there are different approximations that describe the environment around an atom and assign an energy to each atom. And then we can just sum over the energies to get the energy of our whole structures. We can then compare this to properties which can be calculated quantum mechanically, like the vibrational properties or known as phonons, the change of properties when we change the chemical composition, what we see with our convex hull, or the response of the material when we compress it or stretch it, which is measured with a bulk modulus. All these are still properties that are also accessible from the quantum mechanical calculations. But the huge advantage of these machine learning interatomic potentials is really that we can also do much larger simulations, which can then be compared to experiment. And the most important, or one of the most important properties that we want to predict for our experimental colleagues is the dependence of the material in terms of temperature and concentration of alloying elements. So that's typically represented in a phase diagram like we see them here. On the right side, we see the experimental results, and on the left side, we see our prediction from the machine learning interatomic potentials. And while we don't yet have the perfect quantitative agreement, we already see now a very nice qualitative agreement, and we're working we see the clear steps what's required to really achieve also a quantitative agreement. Right? So just to highlight this again, that we are now at the stage where we can use these Python or simulation methods that are typically represented by Python wrappers to then predict materials purely just from the interaction of the electrons, which can be directly compared to experimental properties. That's really the stability of the material in terms of their concentration and temperature. And so having this methodology, the challenge is still that it's a very manual process that involves many different experts. And so during my postdoc, when I was in Los Alamos National Lab and as part of the Exascale Computing Project, we asked ourselves the question, if we have more computing power available, let's say we have a huge exascale allocation, how can we accelerate this process, right? So if compute time is no limiting factor, how can we make it faster? What is typically done is it's a step-by-step process. So you would have one expert doing the quantum mechanical calculation, then they provide their data set to the machine learning expert. The machine learning expert maybe does some hyperparameter optimization, and then we have somebody who is more on the application side, who maybe uses the resulting machine learning model, makes a prediction, and then sees, okay, there's certain parts missing. Maybe we need more quantum mechanical calculation. So that's why we consider this active learning. But it's really a step-by-step process, because first one person finishes the task, and then they hand it over to the next person. What we would like to have is really this kind of streaming workflows, right? So already after, let's say, the first 100 structures are calculated quantum mechanically, we want to start fitting the first interatomic potential. It might not be the best one, but it already helps us to, in the hyperparameter space of our machine learning potential, find the area where we are most likely to find a minimum. And once we have a first guess for the machine learning potential, we can already give it to our active learning person, and they can do the first application simulation and really see how good this model is, right? So, and during the whole process, the quantum mechanical calculation always continues. So we always use the resource for this. We always fit new machine learning potentials, and then we always do the active learning part at the same time. Really, all the processes, all the computational resources are running full power during the full life cycle of this project until we get a result. Right? Rather than step by step, the goal was really to maximize the computational resources that we have available in these large computers. As in particular, also on the exascale machine, you typically don't ask for small allocations, but it should be 100 nodes or more, just to make it easier for them to really schedule these kind of large jobs, the very demanding calculations. And so that's what you see now here. So we see our workflow in terms of like the completed tasks over the runtime of our simulation. And in the beginning, nothing is completed, but already after 10 minutes, the first quantum mechanical calculation finished. So that's where we see here with the increasing blue line. Once they are completed, we also calculate the corresponding descriptors. These are just our representations of the local environments. And once we have, let's say, 100 of those, we start fitting the first potential. So we have 100 structures in our training set, 100 structures in our testing set. So here we can fit our first potential, and then we can use this for validation. And as you see here, right, so we have always an increasing number of computational tasks. And we can then look at this in terms of our target property. In this case, it was how the uncertainty converges over the runtime of this project. So what we see here is basically that already after something like 100 minutes, so roughly 2 hours, we get a potential which we're happy with, which can then be used in larger simulations. So that was a huge success for us in terms of the Exascale project, really saying, okay, we have a large number of small calculations, thousands of different jobs, different tasks, different resources, all bundled into one workflow. But still looking back at it, it was a bit frustrating that it required so much expertise to develop this workflow, right? So it was a very specific workflow, very targeted, very much optimized for this specific application, and it was not very accessible. And that's when we started this challenge of how can we develop a tool that helps now to bring more workflows, more Python functions, more material science to the exascale? How can we make this distribution of Python functions, of calculations on such a large computer much easier? And that's where the idea of executorlib comes from. So we took a step back and thought about looking at the Python standard library. How do we distribute tasks which have no dependence, right? So we can do a simple for loop. And I guess you're all familiar also with the process pool executor, right? So a very common tool to distribute multiple Python functions on our local computer and using all the cores that we have available. The challenge with this is, let me just visualize this here, right? So I have my central Python process, and then I start sub-processes, in this case 4, and each of these is computing, in this example, just the sum of the two numbers. All right, so I can check the status of this, and then I can also get the results from them. Right, so just wait only at this last step when I ask for the result of the future objects. That's the point where it waits until all the calculations are completed. And sure, for the sum, that's very simple, but now imagine this would be a much more complex quantum mechanical calculation, so you would wait more in the order of minutes. So the thread pool and the process pool executors are really nice ways on your local computer or on a workstation to really execute Python functions in an asynchronous way. So really the kind of standard solution. In the same way, we see that modern queuing systems, so there's the Flux framework from Los Alamos National Lab, which is on the one hand a hierarchical scheduler, so you can subdivide your computing allocation into smaller chunks to make it easier to distribute the resources. But on the other hand, they also have a very nice Python interface, which already comes close to this kind of executor style. But rather than submitting Python functions, what they submit are executables or links where we find a script or executable that we want to execute. Right? Again, we can execute this in separate processes, and we can also ask for the result of this computation and see the final result there. So our natural step was, okay, if we now take these two parts together, why can't we just send Python functions to our HPC resources? Right? So let's say I have a large allocation. I want to use something like Flux, but I want to, rather than sending shell scripts and going via shell script for the HPC, I want to be able to directly send Python functions. And that's exactly what executorlib does. For example, for the Flux system, we have this Flux job executor, and the syntax is exactly the same as in the Python standard library. The difference is the processes are no longer on just one compute node, but they can be distributed over hundreds of compute nodes and so on. Right, so really, using the Flux queuing system, we distribute our task over a large number of nodes and make the whole pool of compute nodes behave just like a single computer. In the same way, you can check if your computations are done, or you can check what are the results of this. Right, so it's really, in terms of the user interface, how does a user interact with executorlib? It's the same submit function and map function that the standard library provides, just more specialized for interfacing with the queuing system. On a more schematic way, the goal with executorlib was really to have no additional dependencies, right? So we don't want a database, we don't want a daemon process, we just want the job scheduler to take care of everything. And at the same time, we want to be able to make it very simple for our users to upscale their workflow. So if they start on their local workstation and then go to a local HPC and finally to an exascale machine, the changes should be very minimal. So we have this single node executor where the communication is primarily via sockets. We can also go when we are on the login node of one of these HPC systems and then submit Python functions just by pickling them into an HDF5 file and then distributing them to the job scheduler. If we have a larger allocation, like I showed before, right? So we can say, let's say we have an allocation of 10 compute nodes. We can again use sockets to distribute our functions within this allocation. And this works with the Slurm queuing system, which is currently the most popular one, but also with the Flux system, which is more flexible, in particular for the application on the exascale side. So really, what executorlib allows us is to have the same kind of interface for all the different scales of our workflow, whether we run on local hardware, on a local HPC, or also on an exascale computer. But there's more, right? So as scientists, we have slightly different needs and requirements than somebody who's maybe working in the cloud or working on a data science program. And one of these needs is some codes that use message passing interface to the MPI protocol to synchronize the information. And what executorlib allows you is to only use MPI parallel code within one Python function, while the rest of your program stays a serial Python code. We achieve this by defining this, what we call the resource directory, resource dictionary, where you can provide additional computational resources, like in this case, 2 cores to the function that you submit. So rather than executing this Python function now in a serial Python process, we execute it in an MPI parallel Python process, so to really benefit from the close coupling of the message passing interface. If you now have access to a more advanced job scheduler, like the Flux job executor, you can also assign other resources, right? So we can use CPU cores, we can define threads per CPU call to have OpenMP parallelization, or more recently, we also focus a lot on GPUs, right? So we can request a specific number of GPUs that we want this Python function to be assigned to, right? When you have a large allocation, like these new exascale machines, where we have 8 GPUs on every node, we can specify, okay, what functions get access to the GPU, which function doesn't have access. In the same way, you can assign something like a working directory also to this function in the same way. Right? So just using the resource dictionary to assign the computational resources for a specific function, which allows us then to, for our simulation protocol, not to rewrite the whole protocol, but really rewrite it in terms of individual functions, depending on where you need the more advanced computational resources. The second part that we found is during the development process of such a workflow, in particular when we work on a workstation, many things go wrong, right? And we want to have some cache that outlives the memory of our Python process. So when we run the same process again, it just reloads the result, and we can continue just to see that all the individual steps of our script work correctly together. So also this kind of caching is supported by executorlib for the single node executor as well as the others, where it stores the results in there, and you can even get an overview of the data that's in your cache, just seeing, okay, what were the computations that I already did, what was the runtime, what was the output, and gather the information like this. Right, so again, we use the hierarchical data format, so HDF5 here, that allows us to store multiple calculations and then gather them in a pandas data frame, directly providing them as an input, for example, for a machine learning model. And then finally, if you have now Python functions that depend on each other, maybe one function that takes the input, the output from a previous function, but which have very different computational requirements in terms of computational resources. Let's say we have one function that uses a GPU, while the second function that's maybe MPI parallel. Then you don't want to submit this function just as a single combined function where you write one function around this to the executor, because then it would be blocking the whole resources over the whole time. So we separate those, but we still want to be able to track the dependence of these functions. And that's what I show here, right? So here in the first iteration, my future object is 0, but starting from the second iteration, the future object that I provide is an input. The future object from the previous iteration is an input to the next iteration. So that's also something that executorlib can handle with its executors, and which really allows us to build much more complex structures. You can even visualize the graph of the inputs by just adding the plot dependency graph flag here, and you get this nice network X graph just to visualize what is the dependence of the task that you submit. So with this, because the executor internally waits until the next future is available before scheduling it for execution. So now coming back to the streaming workflow that I showed in the beginning, and where I said we had a very complex code. How far are we now with a library like executorlib to really write this down in a much more simplified way to make it really accessible and decrease the overhead that's required? And just as a reminder, right, so the challenge is we submit 1,000 calculations, they all start running, but we want to take the first 100 of those calculations and bundle them into a batch that is used as a process in the next step. Or maybe if we don't do it with these huge numbers, let's say I have 5 tasks, and I want to batch the first 2 of those that finish first into the first entry, right? So these could be the first ones, let's say task 1.1 and task 1.2, but most likely there's some variation between them, just because of the settings that you choose, the hyperparameters, for example, for your machine learning model. Let's say in this case, the task 1.1 and task 1.4 are the first to finish, and then we have task 1.2 and task 1.5 and so on. And that's the kind of complexity we want to represent in terms of our workflow. So we again start, we build our for loop, we build a list of future objects. This is our list of task 1. And now with executorlib, we have a batched function exactly following the same syntax as the batched function in itertools, but rather than being executed already at when we write down the code, what it basically does, it provides a list of future objects which are then referencing or which are resolved at runtime to the future objects that finish first, right? So I can just have this batched part, and then in task 2, I have exactly the kind of dynamic matching depending on the resources which get completed. And so this really allows us now to build these kind of very complex workflows while having a very simple syntax that, for those of you who are familiar with the standard library, with itertools, feels very natural and really this same kind of standard design. And that's really the key feature of executorlib, trying to follow as close as possible the Python standard library and extending it for the HPC applications. All this is developed as an open source project, and there are certain lessons that we learned from our first project, the pyiron part. Right, so you can find it on the pyiron organization. And the first thing we are very proud of is having really this kind of 97-point coverage. This is not only in terms of unit tests, we also have integration tests. We test the performance of our code, and we also test the typing. So really aiming for stability here was very important to us. And we're particularly proud to also have the integration with the queuing system like Slurm and Flux already integrated in our continuous integration environment. So we really test the whole procedure, how you would use it in production. As a second part, we really like Jupyter notebooks. We use them for documentation, for testing, and for demonstration. And as you can easily guess, these are the same Jupyter notebooks, right? So our Jupyter notebooks are rendered as Jupyter Book for our documentation. We use the same Jupyter notebooks for the integration tests. And when you click on the My Binder link, you get to a virtual environment running in your browser, no installation required, where you can execute the very same Jupyter notebooks. In addition, it also comes with a Flux queuing system, so you can directly try executorlib, how it would behave in a context of an HPC cluster with a job scheduler. In addition, this was also published in the Journal of Open Source Software Science. And as it's a young project, if you like this idea, every star helps, right? So give us a star on GitHub. We would be very happy to get your feedback and try to really grow the community around this, not only inside the material science community, but maybe the more general community here as part of the exchange. So really, the goal was really to have a minimalistic tool that does one thing and only one thing, the upscaling of Python functions, by providing an interface for the job schedulers that we use in the HPC context. With this, I come to my summary. So I hope I was able to give you an introduction into these kind of streaming workflows where we have the dynamic dependencies that are only resolved at runtime. I hope I was able to very briefly explain the underlying framework of executorlib, how the different parts interact with each other, and how we integrate with the job schedulers. So there's no database required, no daemon process. It's just a Python interface to the job schedulers. And then if we go beyond pure Python functions towards really these more complex workflows with dependencies, how this is implemented in executorlib. And with this, I'd like to thank you for your attention.
Fantastic. Thank you so much, Jan. That was an amazing discussion of what executorlib has to offer. Now, I would like to take a moment to introduce our host panelists who are also here joining us. And in this time, if you are in the audience and you have a question, please go ahead and open up that Q&A widget to submit any questions that you can have so that we can include them in part of our panel discussion. First up, I'd like to introduce, or let James Powell introduce himself. James, can you share just a couple of sentences on your Python background?
Hi, everybody. My name is James Powell. And if you're interested in this presentation and you're interested in the other type of simulators, not analytical simulators, but discrete event simulators, I'd love to help you think about that. We're working on a very large project right now to scale the performance of a discrete event simulator by 100-fold.
Fantastic. Excellent. James, next up we have Tom Caswell. So Tom, can you share just a couple of thoughts about yourself?
Hi, I'm Tom Caswell. I'm at Brookhaven National Lab. With my open source hats, I'm the current project lead of Matplotlib and a core developer of H5Py. And I guess I'm happy to talk about plotting, saving files, or running large open source projects.
Excellent. And so with Jan's project here being a young project, I'm sure, Tom, you will have some guidance to share, although Jan is not new to the open source game at all, so to speak. Finally, we have Eugene here with us. Eugene, can you share just a couple of sentences on your background and your Python experience?
Of course. So my name is Eugene. I'm working at the Brookhaven National Lab as well with Tom Caswell, the National Synchrotron Light Source. I have been coding in Python or doing software engineering in Python for about maybe 10 years or so, starting from my postdoc. Here at BNL, I'm mostly doing some work on open source projects for data management, so like Tiled and Blue Sky, and data acquisition, data management. I love everything Python. I would love to talk about improving performance of software and using more Pythonic code and best practices.
Excellent. Well, thank you for joining us today, Eugene. Finally, myself, I'll say my name again. Hello, everyone. I'm Cameron Riddell. And while I've been doing scientific computing in Python for a little over a decade now, I have not done any computations anywhere close to the scale as to what Jan was talking about. So I'm very eager for this discussion to hear about bridging that gap. But without any further ado, let's go ahead and open up our Q&A. Of course, if you are in the audience, please go ahead and submit your questions. And for our host panelists here, what questions do you have for Jan after his discussion?
So can I open with some possibly mean questions?
Yes, let's hear from Tom first.
So, I guess, how do you manage the execution environments for the foreign processes?
So we just copy the environment.
I see.
Now, because the challenge is obviously we could try to reduce it, but we don't find an efficient way to say what the person needs. So we use Cloud Pickle to pickle whatever they have in their current part, like the Python functions and its dependencies. And that's what we transfer over. But then we copy the environment variables from one process to the other to make sure they're able to unpickle this function and load the context.
I see. That means you use Cloud Pickle for the serialization between the processes.
Exactly. So that differs from the standard process pool, but we see that the Cloud Pickle, for example, if you use it inside a Jupyter notebook, it's still able to pickle the function that you dynamically defined, while something like regular pickle fails to work with the process pool in the Jupyter notebooks.
Okay.
And now, James, I saw you had your hand up. Was that on Tom's question here, or was this a new avenue?
It's a new avenue. I have actually quite a number of questions. It was a very interesting presentation, Jan.
Yeah,
if
take it away.
I may start, I actually have a question for Tom and Eugene before we get into this, in part because for all of our host panelists today, we all sit somewhere on the spectrum of simulators. You know, Cameron and I do discrete event simulators. Jan is talking about an analytical physical simulator. And if you think about Blue Sky, it's somewhere in between these two ends. So we all have quite a bit of experience. My first question for Tom and Eugene is there any way within the Blue Sky planification tool, which is itself a simulator of one form or another, to derive the operational graph and then auto-parallelize operations?
No.
Is that something that's ever interesting for Blue Sky? And Jan, for some background, I'm sure Tom or Eugene can give a little bit of background on what Blue Sky is all about, but it's in essence a simulator of another form, but one that actually then derives to real machine operation.
I think with the operations that do produce something like a future, you can manually kick as many off and wait for and basically wait for them to come in, very much like you would with tasks in async IO. And we've not really had a push to pre-compute what those connections would be and run them, and then be able to work on that graph.
There's never a desire to have like two motors and then to figure out how to not serialize them, you move them at the same time to
Yeah,
speed
that's
up
what I was thinking. Like usually when you think about acquisition, at least I think about acquisition, it's kind of one-way process. You just keep acquiring your data, like taking shots and collecting those frames. But yeah, like you mentioned, James, maybe two motors could be an example. Well, Tom, you sure
I
have
think
better idea.
the concern is you'd want to explicitly say I can move these two things together, because from looking at the code, you can say, oh yes, you can move those two motors at the same time, but there's nothing in the code that tells you there's that, one of them is a door and the other is the motor that goes through the door. So you have to,
Right.
Motors this far apart you can obviously move together, but if you have to open the door and move a manipulator arm through, you can't do those. You have to do those in serial, and there's nothing in the representation on the Python side that tells you those physical constraints.
Presumably you could encode that in your hardware abstraction layer, your OFID layer, as it were. But I'm curious if a user facility like your facility is so limited by users being able to access the physical hardware for experimental use, is it not a high priority to speed up how quickly an experiment takes, or is that not the bounding factor? So parallelization doesn't really, I did your beamline experiment twice as fast because I did two things at the same time.
There are some experiments that definitely need to be sped up, but it's at the level of hotspot identification. And typically the way you speed those up would be to push the whole process down a layer in the control system. So either it's a manual thing or a high effort push it down to a fly scan thing. Sorry, that was a whole lot of jargon. I apologize.
Just quick thought. What about those complex experiments that integrate multiple beamlines together when you need to almost like run AI agents to interface between different beamlines and collect data from similar samples, but synchronously, and combine data from multiple beamlines? Could that be a use case or no?
Yes. I think we're well served by just two queues and one agent that can put stuff on both queues.
Yeah.
To tie this to what Jan talked about, Jan, you showed managing dependencies within pyiron. Can you automatically infer dependencies through any mechanism? Or does it always have to be, some kind of counter that you indicate this has to come before that?
Yes, so that's some work that we do now with large language models. To try to say, okay, what is the logical dependence between things? But this is still on a prototype scale, right? So this executorlib is now at the stage where we say, if you know your dependency, we can help you execute this on any scale of computer, from your local workstation to a high performance cluster, or even an exascale machine. And so my question maybe for Tom would also be this: do you have any post-processing steps? So we did some work together with NERSC, and there are definitely groups who do post-processing of large experiments on their on-demand queue. And that's something where I could see something like executorlib being able to, from the Python side, fire up a task at one of the computing centers, which then maybe has multiple processes during the post-processing, could be helpful.
Yes. Yes, there's definitely a opportunity to leverage this to run big jobs on cluster scale compute that currently we are either struggling or very much hero mode making work.
So that would be very interesting for me to get some feedback from that direction. How much, like, we developed this initially for the atomistic simulations, but we really hope that it's something that can also impact other fields. So that's why I'm here to present it, to show, okay, who could maybe benefit from this kind of technology.
If nothing else, for one of my hats at work, I've had to run some jobs on our Storm cluster that involved writing a bunch of hokey bash scripts that I am excited to delete.
Your work, Tom and Eugene, never reaches what would be called exascale. Is that correct?
Not directly.
Okay.
I mean, I don't want to say never, because there, you could imagine having a combinatorial sample where you are driving, you can run and take a measurement on it, and you could imagine folding an exascale simulation of that in, as long as we could get an answer back on a experimentally relevant timescale, to then just run an experiment where you take a measurement, feed the supercomputer says, based on this, the next most interesting point is here, go measure it. And then we go measure that and feed it in, then it drives at the next point. So instead of, basically we can use the measurements to constrain the model and use the model to predict where to go look next on the wafer. And if you want to do that fast, I can imagine you might want to scale up to arbitrary numbers of cores if you have a problem that can scale nicely that way.
If I may, I have a follow-up for Jan going back to the presentation. He shared a slide where he showed the API and the attempts to mimic the concurrent.futures or the thread pool executor API. I'm curious whether you had considered in the design of this to mimic the async IO API, so you could reuse the async IO library and you'd only be responsible for writing your own event loop. Because if you look at, yeah, go ahead.
We looked at this, I guess, where we saw that this nice connection was really for the scheduler, right? So that the scheduler already produces futures, and I think that also async IO would keep my one process busy checking how to resolve the dependence.
That's assuming you're using the built-in async IO event loop. My thought is you use the async IO mechanisms in Python, you write your own event loop that actually then batches these things off to your MPI tasks or whatnot. And so the difference from the perspective of the end user would be, instead of having that context manager with a .submit, you have an asynchronous context manager with an await. And the reason that what I thought about that was, when you look at at least the example context manager, for the most part, the purpose of that context manager is really just to say, don't leave this context until every task is completed.
Yes, I think the other part that we put into the submit are the computational resources, right? So like we would, if you have like one of our quantum mechanical calculations, depending on the input parameters, I might need different computational resources. So we tried these kind of decorator-based approaches to say, okay, I put a decorator on this function, and when I evaluate it, I just internally route it to my execution pipeline, and that didn't work because then it stays the same function. We want to change the computational resources depending on the parameters that the user provides.
Some kind of like elastic data dependent scaling. So it looks at the matrix and then figures out how to.
Yes, or currently it's more static, right? So there's no intelligence the user has to provide for these input parameters. I need this many cores or this many GPUs, but at least they have the option. Because for these quantum mechanical calculations, if your system is slightly bigger, you can need double the compute time or more cores to be able to address this. But in principle, you can use it with the async IO event loop and just integrate the futures there, right? So I guess they also have the complete or wait for completed, and that all works.
So piggybacking off of that question, Jan, I am curious, since I'm presuming you've used your own library for a little bit as well, what are some of the rough edges that you're still kind of working on and thinking of better implementations for?
Yeah. So there's a huge range of different approaches that go into a similar direction. And one use case that we currently don't address is something like what is known in this HPC context as overflow queues. So that basically means if we want to schedule these very big jobs, there's still a bit of resources that are currently unused. So the computing center provides these resources with like lower costs. So we are somewhat charged depending on our proposal. There's a certain credit system, and they provide them with lower quality at the cost that they can kill your job at any time. And that's something that we don't handle nicely yet, so we don't support this, but that's definitely something we want to support in the future. So to really say, you can grow your calculation, you run it on your workstation, then you use this overflow queue as a first way to test it, because when you're anyway on the prototyping stage, you don't need the full reliability, and then you only request your own allocation, like the bigger one, only when you're certain that it works, right? So that's one part we still want to address. On the other hand, every workflow obviously has a certain growing period. So in the beginning, as long as you're local, everything is fine. When you go from local to the HPC system, there's still a little bit, something maybe changes, the executables are somewhere different, so people still need an adjustment time. And the same way when we go from the computing local hardware to the exascale machine, because there's so much more power, you maybe have like more result finishing much more quickly. You need to coordinate this, maybe move the data. Do we want to write to the file system? So there's still a bit of manual tweaking required and not fully automated as we would like to have it, right? So the idea is basically that the app that runs locally can run in the same way on the big machine. There's still a few manual optimizations, but I guess we made a huge jump because previously you really rewrote the code, right? So you wrote it locally using something like process pool executor. You rewrote it using MPI for pi. So everything had to be MPI parallel, always handling which number of core you are. And then you rewrote it again to do MPI for pi with GPU support to be ready to run on an exascale machine. And now you can do this on a per function basis, which makes your code much more modular.
That's very nice features there. To the first feature that you're speaking about, when your jobs could be kind of canceled or killed without you at least being aware, it sounds like solving that portion will also solve one of the other issues that I've seen a lot just with these executor models, and that is, and anything asynchronous, is task cancellation. So it sounds if you solve that, if you solve an external kill, you'll also be able to cleanly kill tasks that are canceled by the actual user as opposed to by the system it's on.
So for our own tasks, we can already kill them. So we have this communication to the job scheduler, but then we know when the killing event takes place. We don't know how frequently do we want to query the central job scheduler, because there are so many users interfacing with this program. We can't query it as much as we query like our local task system, right? So like there are certain constraints, and that's where we still need, we were testing this at the moment. There's a pull request open, but it's not yet in the current release. So that still takes a bit of time, and hopefully in the next version.
Excellent.
So presumably, if you're going to use the overflow queue, either you have to do your own checkpoints within your functions, or you get the whole task or not.
Yes, that would be the first version. Yes. I don't think that
we're distinguishing between like a cooperative kill and a preemptive kill.
Yeah. So some of them give you like a warning. So they say, okay, you now have like 1 minute left. And this can be like, you just get running and they say, okay, in a minute we kill you. Then it's maybe hard to do like a full dump. We have to play around with this, right? So we don't have a solution yet. That's really on the testing side at the moment.
Is this what you would normally use cache for? You mentioned cache in your talk.
Yeah, so the cache we see more in the development phase.
Okay.
When people are on their local workstation where every function call takes quite long and you don't have so many resources to run on in parallel, then you need caching. You write to the file system, that's slow, but you at least can if you restart your program, it can reload where you were before, right? So just getting the first workflow to run through typically still takes maybe a week or something, depending on how familiar the user is, to write, okay, what are the tasks that I want to run? And then we run this in a high throughput campaign thousands, 10,000s of times. So that's where we primarily see the caching.
Related to the task cancellation, there's no notion of cancellation of a blue sky plan, is there? Because the physical analogy there, you can't tell the motor to, you just emit a new message, tell the motor to stop. You don't cancel the plan that was working with the motor.
No, we can throw exceptions in, and when basically there's if the connection bubbles up, we will stop the motors without.
So the equivalent of that is for Jan to have a SSH connection into the nodes and then reboot -now to cancel his tasks.
I can't connect, right? So these are controlled centrally, but yes, there would be. Usually it's more like I lose access to the resource because somebody else gains access, and then they basically kill your whole session and move your part away.
Excellent. I do have one more question, and this is about just a feature that you see across a lot of these job management, job scheduler systems. Is there any way to boot up maybe in a separate Python interpreter or something, kind of like an interface where you can see the status of all the pending jobs? Or are you just left to your own devices and hoping that your code's actually doing something while you wait for your main process to complete?
So we have the option to write error log files, but we don't yet have a status overview panel. That's a bit because we try to be minimalistic and we try to hand this task over to your job scheduler, right? So you can look into your job scheduler and see, okay, do they have a notion what is running, how many resources you're using, and more modern queuing systems. So there's currently a new one brought up in the Berkeley Computing Center, so at NERSC. And they try to provide more statistics of how many resources your different jobs use. But because it's not an easy task in this distributed context, we shied away from this challenge and said, okay, we can write error logs, and we ask you to put log statements in your part and just fill the log if you want to debug it.
Mm-hmm.
But in particular on the large machines, you don't even want to touch the file system, right? So you want to stay in memory as long as possible and only write very rarely to the central file system, because the more compute nodes share one file system, the harder it gets to it, or the slower it gets, right? So you have so many other people accessing the file system at the same time. So it can quickly be the limiting step for these big clusters.
Presumably, since you have a second order modeling of the entire graph, you wouldn't be able to visualize that, but you could visualize at least one unit of the graph. You could have like a little web app with bubbles and whatever. But my guess, Jan, is that would be taking you down the direction of creating a framework, which has like an embedded web app or whatever. And you're not interested in a framework. You're interested in writing a library. Is that correct?
Yeah, I think as soon as you have like web apps and so on, the computing centers are very restrictive. Maybe in particular in these very large systems. So we thought about something simple like a pandas data frame where you just see the status and you can see which tasks are scheduled and what is in the queues. But to get this information, right, so we have to somehow go into the insights. So there's another message on our protocols. It has to propagate through the whole graph. We don't have it yet. We might add it in the future. But I can see the benefit of seeing, okay, yeah, my machine is actually doing something. And it's not just waiting for some small input or to populate all sessions. At the moment, we do it by writing log files and debugging them, and then disabling these log files once we see that the machine is working correctly.
Are you ever interested in taking pyiron and turning it into more of a framework where it comes fully packaged with an answer for how do you solve this problem, how do you solve that problem, how do you do the input, maybe even like a drag and drop, LabVIEW-esque type editor, or is the library where you want to be?
So we now made the step that we modularized the different parts in pyiron. Right? So with this executorlib, we now have the execution part. We have parts for the backend. We have prototypes for something like visual programming. So that's where we extended the Jupyter framework to be able to play around with this. Again, this is not yet on the level that we want to, so it's openly available on GitHub, but we don't have it in our default installation at the moment because there's still certain things that don't work so stable with this. In particular, the HPC integration is one example there. So we see it more of like an ecosystem where the user can pick which components they want. And we're now, again, building it from the ground up to say, okay, the job scheduler that's so central that can maybe also benefit others. And in the same way, we now want to provide different modules of pyiron, like allow people to reuse individual modules without having to buy into the full ecosystem. Because previously we had a rather high barrier for people to enter, and it was very specific to our simulation. So one part of this modularization is also to say, we want to have the science independent from the job scheduling part, so that you can use the science with any other job scheduler as well, so that we can also, our publications can also be leveraged by people who don't use our workflow manager. But obviously there's still a certain motivation to say, okay, if you like our science and you like our tools, then maybe you're also interested in the full package, and that full package would then be pyiron. So I guess in short, pyiron will stay the full package, and then the individual modules are like the entryway into the full part. The libraries are the, yeah.
Excellent. Any final thoughts from or final questions from our hosts?
Ask again, possibly a dangerous political question. Given the recent thrashing of Dask, how do you see this as a possible replacement if that doesn't grow effective community support?
I think I see the communities rather different, right? So like Dask to me is more on the data science side, and they primarily focus on distributing a large number of serial Python tasks, while we see our focus more on the HPC computing side. There are similar tools that also then address the cloud computing market. We are a small team. I'm not sure that we want to compete on that scale. Right? So we compete on the exascale computers because we believe we are, in this context, the fastest. With cloud computing, there are security challenges, there's these web interfaces and so on. That's not where we have a lot of experience, so I'm not sure if we're the right people to develop a solution for this.
See.
It's also much easier to design a complete API for the executors rather than try to mimic the entire API of a pandas data frame. Excellent. Well, if there are no other final thoughts, then why don't we go ahead and adjourn here? I want to thank Jan for joining us. This has been such a fantastic exchange. And I want to remind you all in the audience to keep an eye out for our upcoming exchange. You can do so by visiting our website. That's meetup.doepy.org. So I will share this. If you're a fan of Jupyter, then you're going to want to check out next month. But one final thank you to both Jan as well as our entire host panelists. Thank you all in our audience for joining us, and I hope to see you again next month. Thanks, everyone.